So now we're going to switch over to thermodynamics, which honestly is not that different. It's very common just to hear you say thermo. There's not really a difference between thermochem and thermodynamics. But what we'll be talking about here is what we call favorability. Is the forward reaction or the reverse reaction favored? The first disclaimer I want to give before we get started is that this is not kinetics. If the reaction, the forward reaction, is favored, that doesn't mean it's fast. Some of those can be very slow, and some can be very fast. Okay, they're not related. The second law of thermodynamics tells us that the universe is trying to do two things. It's trying to get the lowest energy possible and the most spread out possible. So if you think about these obvious things that you've seen in the universe, hot objects transfer their heat to cooler ones. Exothermic like combustion are very favorable. Marbles, if you drop a bunch of marbles on the floor, they will roll and scatter, but they're not going to go straight back into the bag. And then jigsaw puzzles. If you break apart a jigsaw puzzle, that's pretty easy, but you're not going to shake it and have it go right back into its pretty little puzzle again. Okay, so you're going to want two main things. Low energy, high entropy, which we haven't talked about yet. So we're going to spend some time on entropy today. Entropy is a measure of the disorder of substances or processes. The more disordered it is, the more favorable it is. So entropy is a measure of the dispersal of matter, how spread out the matter is, how many, we'll say microstates, like how many options does the matter have to be there. So we're going to talk a little bit about entropy first and then go into how this fits into our thermodynamically favorable puzzle. So we'll start here, which has the least amount of entropy. Phases are very important in determining entropy because we're talking about how spread out things are. And you know, for the most part, the solid one, particles are going to be closer together than liquid and then vapor. Okay, so here we're going to say the least amount of energy is going to be our solid water. Gases are much more spread out, so we say they could have more microstates. That's also known as positional possibilities. So if there's more options for the particles to be in, we say there's more microstates, more positional possibilities. So for gases, that's definitely true over liquids and solids. So let's take a look at this question. This one has a little bit of an added trick to it. 1 mole of gold, 1 mole of mercury, are they equal, or is there not enough information? Believe it or not, this is a state of matter question, a phase of matter question, just like the last one. What AP is going to expect you to know here is that mercury is a liquid at room temperature. So gold is going to be a solid, but mercury is a liquid. And that's not typical for a metal. Mercury is a metal, but it is one of those exceptions. And they are going to expect you to know that. They're going to expect you to know, for example, that the halogens are mostly gases at room temperature. Bromine is a liquid. Mercury is a liquid. Those types of things. We'll get more into that later on in the year, but that is why mercury has, question says least. So that is why mercury has the least amount of entropy because it is, I did it again. Gold has the least entropy. I keep answering as if it was most entropy. Gold has the least entropy because it is a solid, where mercury is a liquid, so it would have more entropy. So here, 1 mole of helium at 0 degrees Celsius, 1 mole of helium at 10 Kelvin. Not information, 1 and 2 have the same entropy. So keep in mind that 0 degrees Celsius and 10 Kelvin are very different temperatures, okay? So if it had said 10 degrees Celsius, we might have been able to argue that they're kind of the same. But here, the 0 degrees Celsius and 10 Kelvin, the 10 Kelvin is it's very cold, okay? It's much, much less temperature than 0 degrees Celsius. So for 0 degrees Celsius, it's going to have more entropy because temperature is something that we're going to focus on with entropy. If everything else is the same, a substance at a higher temperature will have more entropy than a lower temperature. So the fact that this is 1 mole in 1 liter gas, both are gas, the only deciding factor here is the temperature, so we would go with the higher temperature. All right. Which graph might best represent entropy changes as temperature increases? Okay, so we have S on the y-axis, temp on the x-axis. So take a look, see what you think. So we're going to go with 3. And I'll tell you why. When the temperature is increasing, the entropy will always be increasing, okay? So we're going to rule this out, rule this out. We're also going to rule this one out because this right here is not increasing with temp. So that leaves us with 3 left. But then the other thing that's going to happen is there's going to be a huge jump when it's changing phase, because we just said temperature relates, but also phase relates. So if you're going from one phase to the other, there's going to be a big vertical jump. We do not have that in this one or this one, so we're going to pick number 3. So here's just a little summary of everything we talked about. This is what you'll be looking for when you're talking about just entropy. So consider phase changes first, especially if gases are involved. But even when it's just liquid versus solid, you want to consider that first. Then look at the moles, which would directly relate to the number of molecules. You're always going to look at gases first. Gases are really important for entropy. But if you have more moles, that's more entropy. If there are what we call conflicting considerations, like you have more moles but they went down to solid or something like that, consider the change in the number of gas molecules as the determining factor. So change in the moles of gas is going to be like your tiebreaker if you need it. So first look at phases, then look at number of moles, and then you can use gases as your tiebreaker. So let's take a look at the ones that entropy will increase for here. So here for this one, we're going from solid to solid and gas. Okay, because we're changing some of it to gas, I'm pretty sure S is going to be positive. Delta S will be positive. However, even if I wasn't sure, I'm going from 1 mole to 2. So this is definitely going to be delta S is positive. Now here, we have all gas molecules, so the phase change doesn't help us. But we have 3 turning into 2. So that one is not going to be delta S is positive. Delta S will be negative there. And the third one, we're going from gas to liquid, so we automatically know that's negative. And then here, we're going from to a solid and a gas to a solid and a gas. So that doesn't tell us anything. But we're going from 5 moles to 7. So if we're going from 5 to 7, that is going to be delta S is positive. So let's talk about actual delta S, what those numbers can be. And what's nice about this is that you're going to use exactly the same thing that we have been using all along, where you take the delta S of the products and you take the entropy of the products and subtract the entropy of the reactants, and that will give you your change in S, because anytime we have delta, it's products minus reactants. So we already know that. So for our delta S, we're going to do S of products minus S of reactants. And you can add the sum signs in there if you want. So here, for our products, we're going to have SO3 is 256. And we have 2 of them. And then we'll subtract the sum of our reactants. So SO2, 249 times 2 plus O2 is 205. When we do that math out, we get 191 joules per mole Kelvin. Now, this is a negative delta S, so check and see if that makes sense to you based on what you just learned. We go from 3 moles of gas to 2. We would expect it to be negative, right? Because we're going in less moles, less gas. So let's do this one. So for this one, we're going to do delta S is equal to our liquid one. So that's 70 minus our gas one, 189. And that's going to give you negative 119 joules per moles Kelvin, which again makes sense. Negative number from going from gas to liquid. So same thing, if you want to pause the video and try this one out, you can absolutely do that. So for CaO, we're going to have 40 and plus CO2, 214. And then we're going to subtract that, 93. And you get a total of positive 161. So let's see if that makes sense. We're going from solid to solid and gas. We're also going from 1 mole to 2. So that makes total sense that it would be a positive delta S. So one more delta S one before we move on to thermodynamic favorability. So here we have 3 FEs, 4 H2Os, and we'll subtract our 146, those 4 H2s, and there we get positive 167. Joules per mole Kelvin. And that again makes sense, positive, because we're going from 5 moles to 7. Okay. So that's delta S, qualitatively and quantitatively. So 2 different things happen to figure out if a reaction is favored. Low energy is favored. So delta H is going to be negative, okay? We're going to release energy, exothermic. That's why combustion ones are so thermodynamically favored. High entropy is favored, meaning that we want more dispersal, more positional possibilities. So for spontaneous processes with unfavorable energy change, the entropy change must be favorable. So here in this situation, delta S is positive because you would be adding to go from solid to liquid. So delta H is positive. Delta S is also positive. So one of those things is favorable and one is unfavorable. So what do we need to actually figure out what the overall favorability is? So that brings us to Gibbs free energy. The Gibbs free energy formula is very important. It will tell us our favorability. Okay, so delta H is part of the question, delta S is part of the question. It's a whole situation, okay? So we use this formula, delta G, and that will tell us if a reaction is thermodynamically favorable or not. If it is negative, it's thermodynamically favorable. If it's positive, it is not. So it's like delta H. We'll talk about delta G being 0 in the next video. So this delta G at standard conditions, 1 atmosphere, 1 molar concentration, just like you would expect delta G to be. It's at 298 Kelvin or 25 degrees Celsius. Okay, you can find these in different tables. You'll see them in your thermodynamic tables. And what's nice is we have this products minus reactants thing still. That hasn't changed because it's still delta. Okay, so here we are going to calculate delta G. You can see the deleted S and T, so you can't use the formula, S and H, excuse me, so you can't use the formula. You're going to use the delta G of formation here. So what you will do is the delta G of the products minus delta G of the reactants. So the products, we have SO2 and O2. And then you're going to subtract 2 SO3s. And when you do that out, you get delta G is positive 140 kilojoules per mole. So that is unfavorable. What that means is that this reaction would actually favor the reverse reaction, where O2 and SO2 are combining to form SO3. That's what we mean when we say unfavorable. So let's take a look. This is that written out a little bit more. What that means, if it's unfavorable, if you put 1 atmosphere of each substance in a container, meaning 1 atmosphere of SO3, 1 of SO2, and 1 of O2, the reaction would not proceed in the forward direction. It would go backwards. If you put only SO3, so only the reactant in our equation up there, a small amount would go forward, but not much, because the reactants are more favorable than the products. So a positive delta G doesn't mean nothing happens. It is unfavorable, so that it means it favors the reactants and not the product. That's all that positive delta G means. It doesn't mean the reaction can't happen. It means that it's not favored. Okay. So now let's take a look at the formula. I'm not going to do too much because it is just a formula that you can plug in stuff, okay? So now we're going to do that with the formula. We already calculated delta S for this equation, and we got 191, negative 191. So now here are delta S form numbers. Negative delta S is unfavorable. Okay, we could calculate delta H. I'm not going to do that out for you. Well, I mean, it's right here. You can see it. Delta H, products minus reactants, would give you positive 196. Okay, we also know that's unfavorable. So we're not shocked that when we put this all together, we get delta G equals delta H minus T delta S Delta H is positive 196 kilojoules per mole. Delta S is positive 191 joules per mole Kelvin. Okay, this brings me to a very important thing for delta G. Delta S is usually given to you in joules per mole Kelvin, and delta H is usually given to you in kilojoules. So in order to subtract them, you have to put them both in the same. Usually what you'll see is that you'll put this into kilojoules. You also need to make sure temperature is in Kelvin, because that will cancel this out, and then you'll have kilojoules per mole, and that we can only subtract things that have the same unit, as you know. Okay, so when I plug in delta S, you'll see that I'll change this to kilojoules. This is often given in joules, but not always. So always make sure you're checking your units, especially on delta S. So when I plug this in, I'm going to do delta H, T, 25 degrees Celsius is 298 Kelvin. And then we'll do 191 for kilojoules per mole Kelvin. And then that's going to give us delta G of 139 positive, which tells us it's unfavorable. And that's essentially the same as what we got up here when we just used the delta G from the table. We got 140, essentially the same. So you can do those either way.